Good afternoon, everyone. I kindly welcome you all to the webinar on synthesis, characterizations, and application of TMDC nanoparticles, organized by Department of Applied Sciences, Parul University. Today we have presence of Dr. Ankur Kumar J. Khimani. He is currently working as an assistant professor in Sri N. Patel Postgraduate Institute of Science and Research. Sir has more than 20 Scopus indexed national and international research papers. He has done his PhD in synthesis, characterization, and application of nanoparticles in 2020 from Sardar Patel University. I warmly welcome you, sir, on behalf of Parul University. Now, I kindly invite you as a speaker for today's webinar. Please, sir, you may begin your session.
Thank you very much for the opportunity. Uh, the title of presentation is Synthesis, Characterization and Application of TMDC Nanoparticle. Thumbnail of the presentation: Introduction to Nanotechnology, Synthesis of Nanoparticle, Characterization of Nanoparticle, in which we will see various characterization of nanoparticle, application of nanoparticle, technology has enormous potential to change the society, and it involves manipulation of object on the atomic level. The product will be built on every atom that are strong, smart, cheaper, cleaner, and more precise. Nanotechnology is the art and science of manipulation matter at the nanoscale to create new and unique material and product. Evolution of nanofield lead to tremendous growth in various areas such as food and agriculture, pharmaceutical, material science, biotechnology, medicine, energy. The surface to volume of nanoparticle is increased because of that only the reactivity is increasing. With the same with nanofluids get and melting point and antimicrobial effect. The reactivity and surface initiates the quantum phenomena which can make nanoparticle unpredictable. Origin of nanotechnology. The Nobel Prize winner Richard Feynman first conceived the idea manufacture in his 1959 speech. There is a plenty of room at the bottom. The Richard Feynman was the first scientist to suggest the device and material could someday be fabricated to atomic specification. Nowadays, we are looking around the atomic specification and we are using various applications. In 1986, K. Eric Drexler wrote Engines of Creation and introduced the term nanotechnology. From the scientist, research really expand over the last decade. Definition of nanotechnology. Nanotechnology involves the understanding and control of matter at nanoscale. The so-called nanoscale deal with the dimension between approximately 1 to 100 nanometer. The nanometer is an extremely small unit of length, a billionth of 10 to power minus 9 a meter. On the nanometer scale, material may exist unusual property. Over here, we can see that the nanoparticle, AG nanoparticle, which possesses the size around 100 nanometer, the color is red. The same nanoparticle AG with the spherical shape. Over here, the shape is changing. It is nanoprism shape and this is sphere shape. So color is changing. Again, Auret nanoparticle, if we take, it is in spherical shape, 100 nanometer. It is yellowish kind of color. The same Auret nanoparticle, sphere in shape, 15 nanometer, color is different. Okay, it is in green in color. So there is a change in optical properties observed as we are going from one size to another size of the same nanoparticle. So on nanometer scale, the material may exhibit unusual property when you change the size of particle. So it can change color, for example. That is because in the nanometer scale particle, the arrangement of the atom reflect the light differently. So gold can appear dark red, purple, white, silver can appear yellowish or amber color. Nanotechnology can increase the surface area of the material. This allows the more atom to interact with other materials. An increased surface area is one of the chief reasons nanometer scale material can be stronger, more durable, and more conductive than their large scale, that is called bulk counterpart. They are subdivided into nanocrystal, nanopowder, and nanotube, subsequently nanoscale C60 atom arranged in long, thin cylindrical structure. Properties of nanomaterials in general. So physical properties, there are various physical properties such as size, shape, specific surface area, aspect ratio, agglomeration, aggregation state, size distribution, surface morphology or topography, structure, include crystallinity and defect structure, solubility. So all the physical parameter can be characterized by various techniques. The same chemical parameters. So structural formula, molecular structure, composition of nanomaterial, including degree of purity, known impurity or additive, phase identity, surface chemistry, composition, charge, tension, reactive site, physical structure, photocatalytic property, zeta potential, hydrophilicity, lipophilicity. So the same can be characterized by various techniques. Nano Is it visible? Is it visible?
Yes, yes.
Okay, sorry for.
Yes, it is.
Okay. Nanomaterial shapes. So nanomaterials can be nanoscale in one dimension, that is surface film, two dimension, that is strands or fiber, three dimension, that is particle. So they can exist in single or fuse form with spherical, tubular, or irregular shapes. Nanomaterial characteristic. So there are three distinct categories. One is one dimension nanomaterial, second is two dimension nanomaterials, third one is three dimension nanomaterial. One dimension includes the layer, multi-layers, thin film, etc. The two dimension includes nanowires, nanofibers, and etc. nanotubes. Three dimension includes they are known as nanoparticle, okay, precipitates, quantum dots. Yes, fabrication of nanostructure. This is very important. Fabrication of nanostructure can be done by two approach. One is bottom to up approach and second is top to down approach. So ultimately we want to reach at nanostructure. So if we have atoms, so atomic scale, if we join together atom by atom and then we can make a nanostructure. Okay. If we have a bulk material and we cut down the bulk material in the small fragments, so ultimately we will get a nanostructure. Okay. But this bottom to up approach is more convenient according to me than the top to down approach. So let us see method of synthesis of nanomaterials. So bottom to up approach and top to down approach. So as far as bottom to up approach is concerned, we have a two distinct category, gas phase as well as liquid phase. In gas phase, by solid precursor, inert gas condensation, pulse laser ablation, spark discharge synthesis, ion sputtering, then spray pyrolysis, flame synthesis, chemical vapor, thermal plasma, and so on. In liquid, there is a co-precipitation, sol gel process, microemulsion, and so on, sonochemical synthesis, and so on. Then top to bottom approach, ball milling, and rest of the other techniques are there, but over here there is an I have not listed. So let us see methods for synthesis of nanostructures. First is sol gel technique. So we have a sol as well as gel. We are mixing together sol and gel, and metal alkoxide we make, and from the metal alkoxide we make gel, and we will have aerogel. So the same we will we can calcinate this and we can make film. Again we can calcinate, we can make it powder, nano powder, and then ceramic film. So these are the applications of nanoparticles: thin film, powder, and then ceramics. So gas phase. So if the particular material is heated, then we can make the cluster of particular gas particle, and we can have a nanoparticle collected on the cold plate. So let us see how high energy ball milling. This is physical approach, bottom to up approach. This is one of the technique from bottom to up approach. So bulk material is loaded into particular this vessel, and in this vessel there are so many carbide balls, and this shaft is rotating continuously for many hours. So the bulk material is come down to the nanomaterials via this technique. So during this time, the tremendous heat is generated to prevent to prevent the heating. The continuous water supply is needed around this particular chamber. So this is physical approach. Arc discharge method. This is again physical approach. So there are two carbon rods. There is cathode and anode. In between two carbon rods, there are two particular positive. This is cathode and anode. Positive charge and negative charge is supplied over here, and you will have a cluster of nanoparticle on particular this side. So this is physical approach. During this growth, the vacuum is needed, gas inlet, the neutral, the argon gas is needed. And you can see the growth from the window. Laser ablation. This is one of the physical techniques. Laser ablation, in which the pulse laser, high intense pulse laser is imposed on the particular target. As a target, you can take a powder of the powder of bulk material. So bulk material, the powder is evaporated in shape of ablation plume, and it is deposited on the particular rotatable substrate holder, and you can scrap the particular deposited nanomaterial or particular deposited thin film. So high vacuum is needed over here. Aerosol synthesis. This is physical method in which we have a precursor solution, and precursor is fed to the particular this type of decomposer nebula, and it is sprayed and sprayed with particular temperature. So you will have this kind of a process. Okay, this is spray flame. So you will have various steps in this flame: dispersion, evaporation of precursor, decomposition, combustion, nucleation, condensation, aggregation, and ultimately you will have a nanoparticle on the top, and you can scrap the particle, and you can characterize the particle for their physical property and chemical property and application. This is again physical method, inert gas condensation. So we have a two crucible. In two crucible, suppose you want to grow CDS nanoparticle. One is full with cadmium, and second one is full with sulfur powder. And the particular amount of temperature is given to the two crucible, and you will have evaporated cadmium and evaporated sulfur. Both will react with each other, and you will have a particular nanoparticle. And this is a liquid nitrogen cold finger. So on the colder side, this particular evaporated gas is condensed, and this is scraper. You can scrap the nanoparticle, and you will have the nanoparticle at the bottom. And this is anvil, Bridgman anvil cell, and via this anvil you can make palette of the particular nanoparticle, and you can characterize the same nanoparticle for their electrical characterization. This is chemical vapor condensation. So over here, the CVD process, where the gaseous precursor react to form the solid coating on the heated surface. So this is furnace, and these are the gas which is fed to the particular chamber, and we will have a reacted gas, and we have this sample. On the sample, you can get deposition of the particular gas films. So application of nanoparticle. So in electronics, nanotransistor, nanodiode, OLED, organic light emitting diode, plasma display, quantum computers we can make. Nowadays we are looking around. We can see various applications of nanoparticle are available. So applications of nanoparticle in energy sector, we can have battery, fuel cell, solar cell. So much research is going on in this field currently. So application of nanoparticle as far as materials are concerned. So nanotubes, aerogel, nanoparticles. So how can this property be used to protect the environment? Ultimately, the application is very important, because if you have any kind of material, if you don't have any kind of application, what is the meaning of this kind of material? So ultimately, application is crucial. So in catalytic property or catalytic application, you can have a better catalytic efficiency through higher surface to volume ratio. So surface to volume ratio plays the very crucial role as far as catalytic property is concerned. Electrical property, increase electrical conductivity in ceramic, magnetic, nanoparticle, nanocomposite, increase electric resistance in metal. So small one atom can change the resistivity of particular material into 10 to power 3, 10 to power 4 order. Okay, there are examples in various books, in various literature. It is stated that magnetic material increase magnetic coercivity up to critical grain size, super paramagnetic behavior. In mechanical, so improve hardness and toughness of the metal and allows ductility and superplasticity of the ceramics. Optical, spectral shift of spectral shift of optical absorption and fluorescence property, increase quantum efficiency of semiconductor crystal. Spherical, increase sensitivity, holosphere of specific drug transport and control release. Biological, increase permeable through biological barrier, membranes, blood-brain barrier, etc. Improve biocompatible. So let us come to the point TMDC. TMDC, that means what? Transition metal dichalcogenide. So over here the structure is shown, transition metal dichalcogenide SNS. So this is symmetric of the 2H SNS2 unit cell with hexagonal symmetry. So in TMDC generally we can see the layers. Generally we found the thin layers. Okay, so transition metal dichalcogenide, which are semiconductor of the type MX2, in which M is transition metal atom such as Mn, Mo, Cr, Ti, V, etc. and Re, and X is chalcogen atom such as S, Se, Se, and sorry, this is repeating. So synthesis, characterization and antimicrobial antioxidant study of facile sonochemically synthesized TMDC, that is SNS2 nanoparticle. So the advantage behind the ultrasonic route of synthesis is ultrasonic treatment prevent agglomeration of the nanoparticle. So many a time agglomeration is disturbing the shape of the nanoparticle, disturbing the property of the nanoparticle. We want nano nature. So agglomeration is not advisable at all. The sonochemical technique is favorable to produce near uniform shape SNS2 nanoparticle. Owing to the energy of the sonochemical waves, the nanoparticle is in particular nano nature. They are not aggregate. So an atom is made to investigate the antimicrobial activity of sonochemically synthesized SNS2 nanoparticle. The other reason for study the tin disulfide or SN, a low toxic element, makes SNS2 a non-toxic or environment-friendly material. The SNS2 is cheap compared to silver, gold, zinc, etc., which have been reported to be good antimicrobial material. So let us see synthesis of nanoparticle, SNS2 nanoparticle. A 300 ml of 0.7 molar 8 gram SnCl4 5H2O solution and 20 ml of HCl are mixed by continuous magnetic stirring for 15 minutes by taking them in 1 liter dry glass beaker. Then a 180 ml of 1.84 molar 25 gram thioacetamide solution is prepared by constant magnetic stirring at 60 degrees Celsius. Then this solution is introduced dropwise to previous solution of SnCl4 5H2O under constant stirring. The stirring and mixing are done for 5 minutes. The prepared solution is placed in ultrasonic bath The specification of ultrasonic bath is Analab bath sonicator with heater frequency 33 kHz, power 50 watts. For 4 hours, the prepared solution underwent gradual changes in color from the transparent to yellow. The yellow precipitates are separated using filter paper. The product is washed with water and methanol subsequently for multiple times. The the particles are oven dried for 10 hours at temperature of 45 degrees Celsius. Then this grown nanoparticle is characterized by EDEX for their chemical identification. The EDEX spectrum of SNS2 nanoparticle is shown over here, the intensity versus energy graph. Over here, the elemental analysis of SNS2 nanoparticle by EDEX. So this is weight percentage and atomic percentage. The EDEX spectrum data shows that the synthesized SNS2 nanoparticle are slightly tin rich but near stoichiometric. The EDEX spectrum show no peak other than Sn and S, thus confirming the synthesized nanoparticle to be free of any other contaminant or impurity. XPS, so further chemical analysis, that is XPS. Intensity versus binding energy graph is given by XPS. So this is the zoom graph. This is intensity of binding energy of the particular 500 to 480 electron volt. The analysis of the spectrum confirms the presence of Sn and S elements in S synthesized nanoparticle. The quality of Sn and S are computed by integral area of XPS peak for Sn 3D and S2P bands. So XPS giving the bands. The molar ratio of Sn and S come out 1:1.96, stating composition to be SNS2. So this confirms we have grown the particular particle. The particle is SNS2 is confirmed by EDEX and XPS. The observed XPS SNS2 substantiate the EDEX result. XRD, the structure of the particular nanoparticle, the structure of the grown nanoparticle has been confirmed by XRD, X-ray diffraction. So over here the intensity versus 2 theta graph. So we get 0, 0, 1, 1, 0, 0, 1, 1, 0, 2, 0, 1 and 0, 0, 5 peaks. All the peaks are matching with the hexagonal phase of SNS2. The observed D-spacing and major peaks are in much with the standard JCPDS card number 230677. The S synthesized SNS2 nanoparticle poses hexagonal crystal structure. The Broden XRD peak state the S synthesized SNS2 are polycrystalline in nature. The determined lattice parameter, that is A equals to B equals to 3.58 angstrom, C equals to 5.88 angstrom. HRTM and SEM. For the morphological investigation, we have done HRTM and SEM, and HRTM gives information about crystallinity also. Okay, so these are the images. A is TM image, B is again the lattice fringe. The TM image, this is particle distribution of this particular image, and this is Assay image, which gives the ring kind of structure. So this state that this is polycrystalline in nature, the grown nanoparticle. So and these two are the same images. The HRTM image clearly shows the synthesized SNS2 nanoparticle to be spherical, having nano size. The particles are precisely packed, possessing partially compact texture with absence of any cracks or pinhole. The lattice fringes come out the crystallinity nature of the particle. The lattice spacing of the fringe is about 0.32 nanometer. This matches with the width 0.33 nanometer of hexagonal structure SNS2 100 plane. The average size of the nanoparticle with standard error comes out 24.04 nanometer, and polydispersity, that is change in the size, that is 10.49%. Both the same micrograph clearly show the nanoparticle to be spherical, are tightly packed, having even distribution, and they have no cracks and pinhole with the even compact distribution. And the spherical shape observed in SEM further corroborates the result in HRTM. So this is UV visible spectroscopy. So optical characterization is done through the UV visible spectroscopy, in which we are getting the absorption versus wavelength graph, and the graph further studied, and we get the band gap of the particular material, and the alpha h nu square versus h nu graph is plotted, and the tangent shows the band gap of the particular nanoparticle is comes out to be 3.71 electron volt. The strong absorption is observed in the wavelength range 335 nanometer and 600 nanometer. The obtained direct optical band gap value is 3.71 electron volt, so relatively higher than bulk SNS2 value 2.24 electron volt, which state the blue shift. The blue shift arises due to the size effect of the nanoparticle. PL spectroscopy, photoillumination spectroscopy, in which we are getting the intensity versus wavelength graph. This is excitation wavelength and this is emission wavelength. So over here, these two graphs are merged. The PL spectrum of the SNS2 nanoparticle synthesized by sonochemical method over here. The multiple PL peak arise due to the presence of crystallinity strain in nanoparticle as observed in XRD analysis. The presence of strong peak at 487 nanometer and 530 nanometer are attributed to the radiative recombination of bound exciton. So this gives about the information of exciton. The few of the peak might be arising due to the slight stoichiometric discrepancy in S synthesized nanoparticle other than strain. Raman spectroscopy. The Raman spectrum of the SNS2 nanoparticle shows the three distinct peaks. First is 3313 centimeter inverse, second is 337 centimeter inverse, and 350 centimeter inverse. The 313 centimeter inverse peak is assigned to A1G mode, that is non-polar, and 337 centimeter inverse mode is assigned due to A2U, that is TO, transfer optical polar mode, and 350 centimeter inverse is A2U, that is LO, polar modes. The first order EG mode peak near 205 centimeter inverse could not be observed in the presence of sample, which may be due to nano size effect. FTIR spectroscopy. The major absorption peak position at 3438.95 centimeter inverse is associated with the symmetric and age stretching vibration of OH group observed water molecule and peak at 1626.20 centimeter inverse, and it is assigned to the bending vibration of the water molecules. Over here, this peak is because of the water molecule, the big peak. Okay, and the broad absorption peak, that is 500 to the 1200 centimeter inverse, are assigned due to SNNS. So the metals peak are observed over here. Thermal analysis. So TGA of the particular sample have been done, and we have the TGA graph, that is weight loss versus temperature. So we have a weight loss in particular three steps. So first is minus 11.70%, second is minus 5.97%, and third one is minus 9.21%. So three steps are observed in particular TGA. So the first weight loss step occur in the temperature range of 308 and 433 Kelvin. So the weight loss arise due to the evaporation of the surface absorbed water molecule from the surface of SNS2 nanoparticle. The second step of weight loss occur in the temperature range of 434 and 654 Kelvin. So this weight loss is ascribed to the decomposition of the residual organic present along with the precursor salt and the release of the sulfur ion from the nanoparticle. The third weight loss step occur in the temperature range 655 and 870 Kelvin. The weight loss is due to decomposition of the nanoparticle at higher temperature. So as far as the temperature increasing, we have the different type of character of the sample is seen. The zeta potential, the stability of the nanoparticle is confirmed by the zeta potential. The zeta potential of SNS2 at different pH is observed. So it is seen that the pH of the 12, the zeta potential comes out to be minus 37 millivolt, while the pH of 2.2, the zeta potential is approximately plus 38 millivolt. The high value of the zeta potential state good stability of the nanoparticle. So for the stability, we have to do zeta potential. And the same nanoparticle is tested for bacterial activity of the nanoparticle. So E. coli, S. aureus, and Bacillus subtilis, that is B. subtilis, are the bacteria taken, and on this bacteria the nanoparticle is tested. So initial inhibitory zone assay for the E. coli MTCC 1687, S. aureus, Staphylococcus aureus MTCC 737, and B. subtilis MTCC 441, employing sonochemical synthesized SNS2 nanoparticle. So you can see the zone of inhibition of the nanoparticle, and this is control of the nanoparticle. So the gap, control minus groups. So agar wall diffuse assay technique is employed for the test SNS2 nanoparticle, show good antibacterial activity against all three studied pathogen microorganism E. coli, S. aureus, and B. subtilis. The S. aureus is gram-positive bacterium possessing thick electron-dense cell wall, which is made up of the teichoic acid, peptidoglycan, and protein. The phosphodiester linkage hold the teichoic acid with the peptidoglycan in cell wall of the bacteria. While B. subtilis is the gram-positive bacterium having thick cell wall and compared of the peptidoglycan. In contrast, E. coli is the gram-negative bacterium in which the peptidoglycan is covered with the extra outer membrane structure. So this membrane structure is anchored non-covalently to the lipoprotein molecule, which are covalently linked to the peptidoglycan. Thus, the lipopolysaccharide, that is LPS, from the part of the outer cell wall of the gram-negative bacteria. This LPS elicites strong immune response leading to the non-interaction of the SNS2 nanoparticle. Again, as far as application part is concerned, we have done antioxidant study. So the antioxidant activity of SNS2 nanoparticle and vitamin C as a reference we took using DPPH assay. So this is percentage radical scavenging activity versus concentration profile. So blue is for SNS2 nanoparticle and C is the reference, that is vitamin C. So free radical scavenging activity is examined via DPPH assay. 500 microliter of the different concentration, 50 to 200 microliter per ml of SNS2 nanoparticle are mixed with the 1000 microliter of DPPH, that is 0.2 millimolar, along with the controlled DPPH, which do not contain any nanoparticle. So this mixture are blend with 3 minutes and dark condition at ambient temperature. Then after 20 minutes, concentration of the radical is examined by reduction in absorption percentage of the mixture at 517 nanometer wavelength. Vitamin C, that is ascorbic acid, is used as the reference. So observe percentage of the radical scavenging activity with response to the concentration of the sample and reference. Vitamin C radical scavenging efficiency of the nanoparticle is found to increase with the increase in the concentration of the SNS2 nanoparticle. The tested SNS2 nanoparticle display more than 60% radical scavenging activity at 200 microgram per ml concentration, which is comparable percentage with that of reference vitamin C activity. The antioxidant activity might be due to the reduction of DPPS by electron donation from nanoparticle sample. The antioxidant potential of nanoparticle could also be attributed to functional group, size, and morphology of nanoparticle. So this is my research, and let us see the advantage of nanoparticle in general. So medical advantages, that is end of illness, universal immunity, body sculpting, stop the aging process, painless childbirth. Then industrial advantages, computer a billion times faster and million times faster, automatic pollution cleanup, and manufacturer at almost no cost. Other advantages, that is architectural, engineering, construction, industry, material producers, uses superior education in textile industry. So these are the advantages of the nanoparticle in various fields nanoparticle are using. What are the disadvantages? So loss of jobs, manufacturing and farming, etc. oil become worthless. We are moving towards advanced nanotechnology. So soon oil becomes worthless. So diamond become worthless. We can synthesize diamond at the lab scale soon. Atomic weapon more accessible and disruptive. So conclusion of the today's talk. So nanotechnology offers the ability to build large number of products that are incredibly powerful. Nanotechnology is heavily intertwined with the biotechnology and information technology, making its scope very wide. The nanotechnology industry is mainly used to create new world. The antimicrobial effect is more in case of S. aureus compared to B. subtilis and E. coli as far as SNS2 nanoparticle is concerned. The antioxidant activity of SNS2 nanoparticle and vitamin C reference using DPPH assay is carried out. The radical scavenging efficiency and nanoparticle is found to rise with the increase in the concentration of SNS2 nanoparticle. The SNS2 nanoparticle displays more than 60% of the radical scavenging activity at 200 microgram per ml concentration, which is comparable percentage with that of the reference vitamin C activity. So from this presented research work, I have done one excellent research paper that is published in a nanostructure and nano object synthesis, characterization, antimicrobial, antioxidant study of the facile sonochemically characterized SNS2 nanoparticle. And these are the references from which I have made the slide. Thank you very much. Thank you very much, Parol University. Thank you very much, Dr. Mohit Tannarana. Thank you very much, organizer, who gave me the opportunity to present my research work and to present my idea regarding nanotechnology. Thank you very much. Do you have any questions regarding today's talk?
Any questions?
Thank you very much.
Thank you so much, Ankur sir, for giving such an informative session and webinar. And thank you everyone for attending this webinar. We end this webinar over here. Thank you everyone.
Thank you. Thank you very much.